In the second video, we're going to explain what enthalpy is. Okay? And to do so, we're going to look at heat. So you're familiar with the definition of heat, the equation Q m delta T Cp. We learned that from last year. Cp is the specific heat. So heat, I said, is a non-state function. In other words, it is path dependent. So let me give you an explanation of why heat is path dependent. Okay? So suppose we got case 1 and case 2. So I've got, actually I'm going to start on the second page so I got more room. So case 1, case 2. So I've got a container and an identical container over here, and I'm going to put 10 grams of propane in there and 10 grams of propane over here, and then I'm going to ignite it and let it explode, and when it explodes it's going to give off heat. So we would expect that the heat given off in the first scenario, case 1, will be equal to the heat given off in scenario 2. And we're going to call this Q prime and Q double prime. So we'd expect that the heat in these two situations would be equal. But I'm telling you that they're not. And then you're like, what do you mean? You have 10 grams of propane in each of these. You ignited them. You've got identical containers. How is the heat released different? The equation is m delta T Cp. They should be equal. Okay? Well, there is one thing that's different between these two containers. In this one, my piston is fixed. What I mean is the piston is not allowed to go up. Whereas in this one, case 1, the piston is allowed to go up. Okay? So we know that the total energy in the universe is conserved, so that the total energy change in both systems must be the same. And sometimes the textbook uses delta E, sometimes a textbook uses the letter U. We're going to use the letter U, okay? So the total energy change must be identical, okay? And delta U is equal to Q plus W, okay? And that actually is the first law of thermodynamics, that the total change in energy is equal to the heat plus the work, okay? So remember the first law of thermodynamics. Okay, so let's go back to case 1. If the piston is going up, my work is going to be negative, right? Because my volume change, and don't confuse V with U here, my volume change is going to be positive, and because work is equal to negative P delta V, that means my work must be negative. Okay? Now, if heat is being released, Q would be negative. So in both scenarios, heat is being released. So in both scenarios, Q must be negative because heat is being released. However, in case 2, what is my work? Well, is my volume changing? No. The volume is 0. So therefore, if the change in volume is 0, my change in work must be 0. So in case 1, I've got I'm going to call it Q prime plus work is equal to Q double prime plus work. Well, in case 1, my work is negative. In case 2, my work is 0. So then how can these two, how can the two sides of the equation be equal? The only way the two sides of the equation can be equal is if remember Q has to be negative, is that Q double prime is a bigger negative number than Q single prime. Okay? So Q prime cannot equal Q double prime. So even though I've got 10 grams of propane, the amount of heat released depends on whether or not the piston is fixed or not. And therefore, you can't just say, oh, I'm going to burn 10 grams of propane. This is the amount of heat that's going to give off when I burn it. It depends on the path you take. So heat is path dependent. Okay? So in case 1, where the piston is allowed to move up and down, the pressure is constant. Because if the pressure starts to go up, the piston goes up to just relieve the pressure. In case 2, what happens to the pressure? The pressure goes up greatly. In fact, case 2, this is actually called a bomb calorimeter. Why? Because if the piston is fixed, sometimes the calorimeter accidentally blew itself apart because the pressure got too high. So we know that just because you have 10 grams of something doesn't mean they're going to give off the same amount of heat. So then that makes it a difficult problem, because if someone were to ask how much heat is given off when I burn 10 grams of propane, the answer is, it depends. Well, that's not very useful. I mean, in science, we want to calculate things. We don't want to say, well, the answer, it depends. So what we do is we agree to measure Q at constant pressure. That is why specific heat is CP. That means for the specific heat, and the P is at constant pressure. So that's why CP is the variable for specific heat, and not the letter S. Some textbooks try to simplify it and they use the letter S for specific heat, but that is not correct. CP is the correct variable for specific heat. So when we calculate Q, what we're doing is we're actually calculating it at constant pressure, okay? Well, I should say this formula is calculating Q at constant pressure, and so we should actually put the little subscript P there for QP, because calculating Q could be case 2, it could be case 1. So if you put a P there, QP, then you know it's at constant pressure. Which brings us to the definition of enthalpy. Enthalpy is heat calculated at constant pressure. So enthalpy, H, is QP. It's H not because heat, but because the Greek word for heat is enthalpy. So we use the letter H. Okay? So now, so when you talk about enthalpy, just think of it as heat. But it's heat measured at constant pressure. Okay? Now, let me give you an analogy as when it comes to measuring enthalpy. measuring heat, okay? So if I were to ask you to measure the height of a mountain, you would say, okay, I can do that. I'm going to put 0 right there, and then I'm going to measure the height of my mountain, and this mountain just happens to be 3,000 meters tall, okay? And I'm right here at 1,000 meters, and I'm going to climb up to 2,500 meters. So what is my change in altitude? Well, if I'm here and I go to there, my change in altitude is 1,500 meters, okay? Now, is that the only way you can number a mountain? No, you don't have to put the 0 at the bottom. You could, if you really wanted to, put the 0 at the top, and then this would be negative 3,000, and then this would be 1,000, and then this would be 2,500, negative, negative. I'd still get the same change in altitude. It would just be a negative value. So you can put that either way, okay? It doesn't really matter whether you put the 0 at the top or the bottom of the mountain. The change will be the same. Now, the thing with enthalpy mountain is that there is no top to enthalpy mountain. It just keeps going on forever and ever and ever. Okay? So it's kind of like saying, how much money can you gain? Well, there's no limit to the amount of money you can gain. And similarly, there's no limit to the amount of money you can lose. So what can you do? How can you measure your mountain if you don't have a top and you don't have a bottom? Well, you pick an arbitrary 0 point, okay? And that arbitrary 0 point is elements in their most common state have an enthalpy of 0. In other words, they have a delta H of 0 kilojoules per mole. Okay? We put a little degree symbol there. The little degree symbol means at 25 degrees Celsius and 1 atmosphere, which is called standard conditions. Okay? Don't get that confused with standard temperature and pressure, which is 0 degrees Celsius. Standard conditions is 25 degrees Celsius and 1 atmosphere. So you might be saying, well, how can they just arbitrarily pick a point? Well, we do that with mountains as well. We arbitrarily picked sea level as the 0 point. If you pick sea level as the 0 point, the tallest mountain in the world is Everest at like 25,000 feet. But if you pick the bottom of the ocean as your 0 point, then the Hawaiian Islands are actually the tallest mountains on the planet at about 35,000 feet, because about 15,000 feet of the Hawaiian Islands lies below the water. So it all depends on your perspective. And so science has arbitrarily said we're going to put elements in their most common state at 25 degrees Celsius and 1 atmosphere has an enthalpy of 0. And everything will get measured off of that. Now the beauty of that is it doesn't change your delta. Okay? So even if we were to pick a different 0 point and these numbers changed, suppose this became 2,000, well, this would just become 3,500. So the delta always remains the same no matter what you're picking as your 0 point. Okay? So that is why it's delta H, not H, that we're measuring. Okay? So what is the enthalpy of formation, delta HF? The F stands for formation. What is the enthalpy of formation of hydrogen gas? Well, is hydrogen an element? Is its most common state gaseous form? Is its most common state diatomic? Yes, yes, and yes. So the enthalpy of formation, in other words, meaning how much energy does it take to form, is 0. What is the enthalpy of formation of solid gold? Well, is the most common state of gold a solid? Yes. Is it an element? Yes. So it's 0. Okay? So what about the enthalpy of formation of liquid gold? Is gold normally a liquid? No. So guess what? You're going to have to put energy into this. So to turn from a solid to a liquid, you're going to have to put energy in. So delta H would be a positive value. So if delta H is positive, you're putting heat in, and we would say it's endothermic. If delta H is negative, heat is being released, and we would say it's exothermic. Okay, so that's enough for today, and then tomorrow we will work on what is delta H of reaction and learn how to calculate that.